March 31, 1945, Rhine-Main Airfield, Germany. The war in Europe was crumbling toward its inevitable conclusion. Berlin burned. German armies retreated on all fronts. Yet on this particular spring morning, something extraordinary was about to happen that would change aviation history forever. A sleek, shark-like aircraft touched down on the runway. Its swept wings gleamed in the pale sunlight. No propeller spun at its nose. Instead, two strange cylindrical pods hung beneath those wings, pods that would soon reveal secrets the Allies had desperately sought for years. The pilot who emerged from the cockpit was a German test pilot named Hans Fey. Unlike the thousands of his countrymen who continued fighting, Fey had made a choice. He had defected, and he had brought with him something priceless: Messerschmitt Me-262, serial number 11711, the world's first operational jet fighter, fresh from the factory, unpainted, perfect. American intelligence officers swarmed the aircraft within minutes. They circled it like archaeologists discovering an unknown civilization, because in many ways, that's exactly what this was. A glimpse into the future, a future where propellers would become obsolete, where the roar of reciprocating engines would give way to the banshee scream of the jet. But no one that morning, not even the most experienced aviation engineers present, could have predicted what they would discover when they began their examination of those mysterious engines. What they would learn would both astound them and terrify them in equal measure. This is the story of that discovery. To understand what American engineers found when they examined that captured Me-262, we need to step back several years, back to a time when jet propulsion existed only in the fevered imaginations of a handful of visionary engineers and the pages of science fiction pulp magazines. The late 1930s, Germany, Britain, and the United States were all independently pursuing jet engine technology. But Germany had advantages, desperate advantages, born from Adolf Hitler's rearmament program. The German Air Ministry, the Reichsluftfahrtministerium, understood that conventional piston engines had limitations, fundamental limitations that no amount of engineering brilliance could overcome. Two men would become critical to Germany's jet program: Hans von Ohain and Anselm Franz. Von Ohain, working with Heinkel, would create the first practical jet engine, the He-3, which powered the Heinkel He-178 on the world's first jet-powered flight on August 27, 1939, days before Germany invaded Poland, days before the world descended into total war. But it was Anselm Franz who would create the engine that American engineers would later examine with such fascination and dread. Franz worked for Junkers, one of Germany's premier aircraft engine manufacturers. In 1939, he was given a seemingly impossible task: create a mass-producible turbojet engine, not a laboratory curiosity, not an experimental prototype, but a real engine that could power real combat aircraft. The technical challenges were staggering. Inside a turbojet engine, temperatures reached nearly 2,000 degrees Fahrenheit. Metal components spun at tens of thousands of revolutions per minute. The forces involved were enormous. The materials required were exotic: nickel, chromium, cobalt, molybdenum. Franz assembled a small team at Junkers' facility in Dessau. They were young engineers, mostly fresh from university. Germany's experienced piston engine specialists couldn't be spared. They were too valuable, keeping the Luftwaffe's conventional fighters and bombers in the air. So Franz trained his rookies. He taught them. He pushed them to think differently, to abandon everything they knew about piston engines, and embrace an entirely new paradigm of propulsion. What they created was the Junkers Jumo Original 4. The designation came from the Reich Air Ministry's numbering system. The 109 prefix indicated a reaction engine project. The 004 was simply the fourth jet engine project Germany pursued. The Jumo 4 was revolutionary. Unlike earlier jet designs that used centrifugal compressors, the Jumo 4 employed an axial flow compressor. 8 stages of compressor blades, each stage increasing the pressure of the incoming air. The compressed air then mixed with fuel in 6 combustion chambers, ignited, and blasted through a single-stage turbine before screaming out the exhaust nozzle. On paper, it was elegant, simple, efficient. In reality, it was a nightmare of compromises. The first Jumo 004A engines performed well in testing. They produced the required thrust. They ran smoothly. They showed promise. But there was a problem. a massive, insurmountable problem that would haunt the engine throughout its operational life. Those early engines required enormous quantities of rare metals, nickel, cobalt, chromium, molybdenum. By 1943, Germany's access to these strategic materials had evaporated. Allied bombing had disrupted supply lines. Naval blockades prevented imports. The existing stockpiles were reserved for other critical war industries. Franz faced an impossible choice: abandon the jet engine program entirely or redesign the Jumo to use materials Germany actually had. He chose the latter. The Jumo B, the production version, represented one of the most audacious engineering gambles of the Second World War. Franz and his team replaced virtually every critical component with inferior substitutes. The turbine blades, which had been solid nickel alloy in the E04A, were now made from a steel alloy called chromadur. It contained only 12% chromium, 18% manganese, and the rest was simple iron. The combustion chambers, originally constructed from heat-resistant nickel alloys, were now mild steel protected only by a thin aluminum coating. The compressor blades went from sophisticated alloys to stamped aluminum and pressed steel. It shouldn't have worked. By every conventional engineering principle, it should have been a disaster, but it did work. Barely. The Jumo B produced thrust. It powered the Me-262. It made jet combat a reality, but it came with a price. A terrible price that German pilots would pay with their lives, and that American engineers would discover with mounting horror when they examined the captured examples. While Franz struggled with his engines, Messerschmitt was developing the airframe that would carry them. The Me-262 project, known internally as Project 1065, began in April 1939. Willy Messerschmitt and his chief designer, Waldemar Voigt, envisioned a radical aircraft: swept wings for high-speed flight, tricycle landing gear for better ground handling, two engines for safety and power. The first prototype, the Me-262V1, took to the air on April 18, 1941. But in a twist of historical irony, it flew with a conventional piston engine in its nose. The jet engines weren't ready yet. They weren't reliable, so Messerschmitt hedged his bets. It wasn't until July 18, 1942, that the Me-262 flew purely on jet power. Test pilot Fritz Wendel lifted off from Leipheim Airfield. The Jumo 04 engines howled. The aircraft accelerated with shocking speed. For the first time, humanity experienced pure jet flight in a practical combat aircraft. But the path from that first flight to operational deployment was agonizingly long. Hermann Göring, head of the Luftwaffe, didn't initially support the jet program. He preferred investing in proven piston engine designs. Adolf Hitler, when he first saw the Me-262 in May 1943, immediately demanded it be developed as a bomber, not a fighter. This single decision delayed the jet fighter program by crucial months. It wasn't until fighter ace Adolf Galland flew the Me-262 and declared it superior to anything the Allies possessed that serious production began. By then, it was 1944. The Allies had landed at Normandy. Germany was running out of time. Production of the Me-262 faced enormous challenges. Allied bombing had destroyed the Messerschmitt factory at Regensburg. Production shifted to dispersed facilities, including underground tunnels and forest clearings. Skilled workers were scarce. Materials were in short supply. Each aircraft required hundreds of hours to assemble, often by forced laborers working in terrible conditions. Despite everything, Messerschmitt managed to build over 1,400 Me-262Zs by war's end, but only a fraction ever saw combat. Many sat on airfields waiting for engines that never arrived. Others were destroyed by Allied bombing before they could fly. Still others broke down due to mechanical failures before they could engage the enemy. For the Allied pilots who did encounter the Me-262 in combat, it was a revelation and a nightmare. Lieutenant Urban Drew of the 361st Fighter Group was flying his P-51 Mustang on October 7, 1944, when he spotted two Me-262s taking off from an airfield near Osnabrück. Drew dove on them immediately, catching one jet while it was still slow and vulnerable during its climb out. His guns hammered. The Me-262 caught fire and went down. Drew had scored one of the first confirmed victories over a jet aircraft, but Drew was lucky. He caught the jet at its most vulnerable moment. Once the Me-262 reached its operational speed of over 500 miles per hour, conventional fighters couldn't touch it. Captain Chuck Yeager, who would later become the first man to break the sound barrier, encountered an Me-262 in November 1944. Yeager was flying his Mustang at 26,000 feet when he spotted the jet far below. He pushed over into a dive, his Mustang screaming downward. The Me-262 pilot never saw him coming. Yeager fired from close range and the jet disintegrated. But again, this was circumstance. The jet pilot was distracted, unaware. Once an Me-262 pilot knew you were there and used his aircraft's performance, you couldn't catch him. You couldn't outrun him. You couldn't outclimb him. American bomber crews learned to dread the distinctive sound of the Me-262's approach. The jet would streak through a bomber formation at speeds over 500 miles per hour, its four 30mm cannons tearing B-17s and B-24s apart. Then it would be gone before the gunners could track it. Seconds later, it would attack again from a different angle. On March 18, 1945, Me-262s intercepted a large American bomber formation. In minutes, they shot down 12 bombers while losing only 3 jets. It was one of the most lopsided aerial victories of the war. But these victories came too late. By early 1945, Germany was collapsing. Fuel was scarce. Pilots were undertrained. The Me-262, revolutionary as it was, couldn't change the outcome of the war. What it could do, however, was change the future of aviation. If the Allies could capture these jets and learn their secrets. Enter Colonel Harold Watson and Operation Lusty. Watson was a test pilot and aeronautical engineer from Wright Field, Ohio. In early 1945, he received orders directly from General Karl Spaatz. Find Germany's advanced aviation technology, capture it, bring it back to the United States at any cost. Watson assembled a team of pilots, engineers, and maintenance personnel. They called themselves Watson's Whizzers. Armed with Eisenhower's personal authorization to commandeer any resources they needed, the Whizzers began trolling across Europe as the war wound down, searching for German wonder weapons. Their primary target was the Me-262. Intelligence reports indicated that Lechfeld Airfield, near Augsburg in southern Germany, housed numerous Me-262s, including the rare two-seat trainer variants. The Whizzers raced to reach Lechfeld before the Soviets could get there first. They arrived on May 3, 1945, 5 days before Germany's surrender. What they found exceeded their expectations. 25 Me-262s sat on the airfield. Most were intact. Some were even flyable. And wonder of wonders, several German test pilots and technicians were still at the field, willing to cooperate. Among them was Ludwig Hoffmann, a Messerschmitt test pilot who had trained Luftwaffe pilots on the Me-262, and Karl Bauer, Messerschmitt's chief test pilot. These men possessed knowledge that couldn't be found in any manual or technical document. Watson made them an offer: help us or go to a prisoner of war camp. They chose to help. Over the next several weeks, the Whizzers and their German assistants worked frantically to prepare the Me-262s for flight. They scavenged parts from damaged aircraft. They improvised repairs. They trained American pilots who had never flown jets before. The training was harrowing. The Me-262 was unforgiving. Its engines took nearly 2 minutes to spool up to full power. If you advanced the throttles too quickly, the engines would flame out or catch fire. If you landed too fast, the landing gear would collapse. If you ran the engines too long, they would simply disintegrate. But the American pilots learned, and starting in early June, they began ferrying the captured Me-262s across Germany to Cherbourg, France. Each flight was a risk. These were worn aircraft with tired engines, flown by pilots with minimal jet experience over territory that might still harbor hostile forces. Several aircraft were lost, some to mechanical failure, others to pilot error. One Me-262 crashed when both engines caught fire simultaneously, forcing the American pilot to bail out, but most made it. By mid-July 1945, the Whizzers had gathered an extraordinary collection of German aircraft at Cherbourg, including at least 10 Me-262s. The British loaned them an escort carrier, HMS Reaper, and on July 19th the ship departed for the United States, its hangar deck packed with the most advanced aircraft in the world. The jets arrived at Newark Army Airfield on July 26, 1945. From there they went to Wright Field in Dayton, Ohio, and Freeman Field in Indiana, where American engineers could finally begin their detailed examination. What they discovered would shock them. The examining team at Wright Field's Air Technical Intelligence Division approached the Me-262 systematically. They photographed every component. They measured every dimension. They tested every system. And when they removed the engine cowlings and began examining the Jumo 04 turbojets, they understood immediately why German pilots had such a high accident rate. The engines were brilliant and terrible in equal measure. Engineer Roy Adams led the technical analysis. His February 1947 report, titled Evaluation of the Me-262, documented findings that ranged from impressive to horrifying. The axial flow compressor design was decades ahead of contemporary Allied efforts. The British Whittle engines and early American jets used centrifugal compressors, which were less efficient and larger. The Jumo 04's 8-stage axial compressor was compact, powerful, and elegant. But the materials, dear God, the materials! When metallurgists analyzed the turbine blades, they discovered what Franz had been forced to do. The blades were made from chromadur, an inferior steel alloy. Under a microscope, the engineers could see hairline cracks throughout the metal structure, capillary fractures that formed during manufacturing and worsened with every hour of operation. The combustion chambers showed extensive heat damage. The thin aluminum coating that protected the mild steel underneath had burned away in most examples. The steel itself showed warping and stress fractures. The compressor blades were stamped aluminum for the first 2 stages, pressed steel for the remainder. Many showed signs of foreign object damage where debris had impacted them during operation. The attachment points were crude, held by small screws that frequently worked loose due to vibration. The engineers ran bench tests on captured engines. They monitored temperatures, pressures, vibrations. What they discovered explained everything. The average operational life of a Jumo 04B engine was between 15 and 25 hours, not hundreds of hours like a good piston engine, not even 50 hours. 15 to 25 hours before the turbine blades failed, or the combustion chambers burned through, or the compressor self-destructed. Some engines barely made it to 10 hours before requiring complete overhaul. A few exceptional examples might last 40 hours, but that was rare, very rare. German pilots were essentially flying aircraft with time bombs strapped to the wings. The failure modes were particularly dangerous. When turbine blades failed at high speed, the disintegrating fragments would often punch through the engine casing, causing catastrophic fires. When combustion chambers burned through, jets of flame would shoot backward into the tail section, igniting hydraulic lines and control cables. The Americans discovered records showing that more Me-262s had been lost to engine failures than to enemy action. Pilots taking off would suddenly find one engine failing, or both. They would have seconds to react. Many didn't make it. But here was the truly terrifying realization. Despite all these flaws, despite the horrible materials and the constant failures, the Jumo 04 worked. It worked well enough to power the world's first operational jet fighter. It worked well enough that Me-262 pilots shot down over 500 Allied aircraft. It worked well enough that a single Me-262 could tear through a bomber formation that a dozen conventional fighters couldn't touch. What would happen if these engines were built with proper materials, with good alloys, with precision manufacturing? The answer was obvious and frightening. The American engineers calculated that a properly built version of the Jumo 04, using the materials Franz originally specified, could achieve operational lives of hundreds of hours, maybe more. It would be reliable, powerful, revolutionary. The swept-wing design design of the Me-262, the engineers discovered, was equally advanced. The aircraft remained stable and controllable at speeds approaching Mach 0.88, far faster than any Allied fighter. The British Meteor, the only other operational Allied jet, became dangerously unstable above 750 kilometers per hour. The Me-262's wing design would directly influence the North American F-86 Sabre, which would dominate the skies over Korea just 5 years later. The Boeing B-47 Stratojet bomber would use a nearly identical swept-wing configuration. The entire architecture of Cold War jet aviation owed its existence to Messerschmitt's design, but it was the engine that obsessed American engineers. The Air Technical Intelligence team at Wright Field pulled in engine specialists from Pratt & Whitney, General Electric, and Westinghouse. These were men who had been struggling for years to create viable jet engines for American fighters. They had seen Frank Whittle's centrifugal designs. They had examined captured documents, but nothing prepared them for the elegant simplicity and audacious engineering of the UMO Series EO4. Dr. Anselm Franz, who had designed the engine, was eventually brought to the United States as part of Operation Paperclip, the program to recruit German scientists. He would spend decades working for American companies, eventually developing the T-53 and T-55 turboshaft engines for Lycoming. Those engines would power countless helicopters, including the famous Huey that defined the Vietnam War. The test pilots who flew the captured Me-262s at Wright Field had mixed reactions. The aircraft was faster than anything they had flown, much faster. One pilot described the acceleration as being hit in the back by a giant invisible hand. Another said it felt like riding a rocket, but the engines were temperamental, unpredictable, dangerous. Captain Eric Brown, a British test pilot who would eventually fly 487 different aircraft types during his career, called the Me-262 the most formidable aircraft of World War II. But he also noted its terrible reliability. He personally experienced 2 engine failures during his evaluation flight. The comparison tests between the Me-262 and the American P-80 Shooting Star were particularly revealing. On paper, the P-80 should have been superior. It was newer, built with better materials, more reliable. But the Me-262 handled better at high speeds. Its acceleration was superior. Its weapons were more powerful. The German jet, despite all its flaws, remained a better fighter. Only the engine reliability gave the P-80 an advantage, and that advantage came purely from America's access to proper materials and manufacturing techniques. Soviet engineers who had captured numerous Me-262s when the Red Army overran Germany, reached similar conclusions. They reverse-engineered the Jumo Vorher and produced it as the RD-10. The Soviet-built engines were even less reliable than the German originals, averaging only 10 to 12 hours before failure. The Soviets installed RD-10 engines in their first jet fighters, the MiG-9 and Yak-15. These aircraft entered service in 1946, giving the Soviet Union a jet-powered air force years before they might otherwise have achieved it. By 1947, American, British, and Soviet engineers had all thoroughly examined the Me-262 and its engines. The lessons learned would shape jet aviation for the next decade. The axial flow compressor became standard on nearly all jet engines. The swept wing became ubiquitous. Even specific details like the variable geometry exhaust nozzle the Jumo 004 used found their way into production engines worldwide. But the deeper lesson was more subtle and more important. Anselm Franz and his tiny team of inexperienced engineers, working under impossible conditions with terrible materials and constant Allied bombing, had created an engine that should not have worked. They had pushed the boundaries of what was technically possible. They had accepted compromises that no peacetime engineer would consider, and they had produced something that worked, not well, not reliably, but well enough. That willingness to accept short operational life in exchange for revolutionary performance would echo through military aviation development for decades. The SR-71 Blackbird's engines, which required complete overhaul after relatively few hours of operation. The early turbofan engines that powered the F-14 Tomcat, which struggled with reliability for years. The acceptance that cutting-edge performance often came with cutting-edge risk. The Germans had shown that it could be done, that you could build an operational jet fighter, that the future was possible, even if that future was dangerous and unpredictable and terrifying. Back at Wright Field in 1946, the examination of the Me-262s continued for months. Every detail was documented, every innovation studied, every flaw cataloged. One by one, the captured jets were retired from flight testing as their engines failed. Some were preserved for museums, others were used for ground testing until they fell apart. A few were simply scrapped when they became too dangerous to maintain, but their influence never faded. When American engineers designed the engines for the F-86 Sabre, they incorporated lessons learned from the Jumo 04. When Boeing designed the B-47 bomber, they copied the Me-262's wing sweep and engine placement. When Lockheed designed the F-104 Starfighter, they studied German research into high-speed flight that had been captured at war's end. The Me-262 itself, that first operational jet fighter, lives on in museums around the world. The National Air and Space Museum in Washington displays one. The National Museum of the United States Air Force in Dayton shows another. The National Naval Aviation Museum in Pensacola has the two-seat trainer that Watson's whizzers called Vera. These preserved aircraft stand as monuments to human ingenuity and human desperation. They represent what can be achieved when brilliant minds push the boundaries of the possible, and what happens when those boundaries are pushed too far too fast with too few resources. In the end, the story of the Me-262 and the Jumo 04 is not really about German engineering superiority. It's about what happens when you try to build the future with the scraps of the present. It's about the price of innovation under impossible circumstances. It's about the thin line between breakthrough and catastrophe. Those American engineers who examined that first captured Me-262 in March 1945 understood this. When they removed the engine cowlings and saw the crude materials and desperate compromises, they didn't just see German failures. They saw possibilities. They saw what could be done with proper resources, with good materials, with time and testing and refinement. They saw the future, and it both excited and terrified them. Because if Germany, broken and bombed and starving, could build this, what could be achieved by a nation with unlimited resources? What would jet fighters look like in 5 years, 10 years, 20? The answer would come soon enough. The F-86 Sabre would fly in 1947. The MiG-15 would fly in 1947. The British Hawker Hunter would fly in 1951. Each generation faster, more capable, more refined. But they all owed their existence to those desperate German engineers working in underground factories, to Franz and his team creating engines from materials that shouldn't work, to Messerschmitt and Voigt designing airframes for speeds no one had reached, to the test pilots who risked their lives flying aircraft that might explode at any moment. The jet age began not with a triumph, but with a compromise, not with perfection, but with good enough, not with unlimited resources, but with whatever could be scraped together in the ruins of a collapsing empire. And when those American engineers finished their examination and wrote their reports, they concluded with a simple statement that would guide military aviation development for decades to come. The Me-262 proved that jet fighters were not just possible, they were inevitable. The propeller age was over. The future had arrived. It had arrived damaged, flawed, dangerous, but it had arrived, and there was no going back. Today, nearly 80 years after that first captured Me-262 touched down at Rhine, Maine, we live in a world where jet propulsion is ubiquitous, where commercial airliners routinely cruise at speeds the Me-262 could barely reach, where military fighters exceed Mach 2 with ease. But none of it would have happened the way it did without that desperate gamble by Anselm Franz, without his willingness to build an engine from inferior materials and accept a 25-hour operational life, without Messerschmitt's radical swept-wing design, without the thousands of nameless German workers who assembled these aircraft in tunnels and forests while bombs fell overhead. And it certainly wouldn't have happened without Watson's whizzers who risked everything to capture these jets and bring them home, without the American engineers who painstakingly documented every detail, without the test pilots who flew these temperamental machines knowing they might not survive the landing. The Me-262 changed everything. It proved that the future was possible, even if if that future was built on a foundation of compromises and desperate measures. The next time you see a jet aircraft, any jet aircraft, remember that somewhere in its DNA is a piece of the Me-262, a fragment of that revolutionary design, an echo of those Jumo 004 engines screaming at full power. And remember, too, the engineers who examined those captured engines with growing amazement and dread, who understood that they were holding the future in their hands, a future that was simultaneously wonderful and terrible, inspiring and frightening. They documented everything, they learned everything, and then they used those lessons to build something better. That's the real story of the Me-262. Not that it was a super weapon that could have won the war for Germany. It couldn't. It was too late, too unreliable, too few in number, but it was a glimpse of tomorrow, a preview of the jet age that would transform human civilization. And sometimes a glimpse is all you need to change everything.